Good afternoon. I am Dr. Dhananjay Kumar Tripathi, an assistant professor of physics under the Department of Basic Science and Humanities. So today we will learn angle between two planes. You just recall that in the last class we have discussed the Miller indices. Miller indices are the indices which used to represent a plane, and these Miller indices are always given in terms of HK and L numerals. So here, if we take the two planes, one with Miller indices H1, K1 and L1 and other with S2, K2, L2, then the unit normal vector to the plane H1, K1, L1 will be given by N1 unit vector is equal to H1 by A into I1 plus K1 by B into J1 plus L1 by C into K1 divided by under root H1 by A square plus K1 by B square plus L1 by C square. Now for any cubic system, we know that A is equal to B is equal to C. So because of that, the unit normal vector to the plane H1, K1, L1 will be I H1 plus J K1 plus K L1 by under root H1 square plus K1 square plus L1 square. Similarly, the unit normal vector to the plane S2 K2 L2 can be written using the earlier concept. N2 will be equal to IS2 plus JK2 plus KL2 divided by under root H2 square plus K2 square plus L2 square. Now the product of these two unit vectors will be taken. So the product of these two unit vectors dot product will be what? The magnitude of unit vector n1 into the magnitude of unit vector n2 into cos of theta. Now we put their values. So because of that, we will be able to find out theta will be equal to cos inverse h1 into L1, h1 into L1, h1 into s2 plus k1 into k2 plus l1 into l2 by under root h1 square plus k1 square plus l1 square into s2 square plus k2 square into l2 square. Now this is the angle between any two planes. Now we want to confirm this theory with the help of some numerical problems. Just in the last class, I told you that theory is always confirmed with the help of the numerical problems. So here we will do the same thing. For that, we have taken the first problem. The first problem is calculate the number of atoms per unit area of a plane 1, 1, 1. That means the value of H, K and L is 1, 1, 1 plane in a simple cubic structure. So the area of plane is half into base into height. Now let us take a this is a triangle which is showing a plane. Okay, this is a plane. So in this plane, we are getting the triangle as EDG, which we have redrawn here. So EDG is the triangle. So here this area of plane will be what? Half into base. Half into base. This base is root 2a into height EU. So our task is to find out this EU. This EU is serving as the perpendicular on the line DG. So because of that, this will be a right angle triangle. If this will be a right angle triangle, then cos DEO, DEO, this one, this is 30 degree and cos theta is equal to B by H. So because of that, EO by root 2A, EO by root 2A. Due to that, EO will be written as root 2A into cos 30. Now cos 30. So root 2a into cos 30, that is 0.866. So because of that, area of the plane will be what? Half into base. Base is root 2a and height we have calculated root 2a into 0.866. So because of that, the area of the plane will be 0.866 a square. So total number of atoms in this plane will be what? Total number of atoms. So that will be half into base into height that we have written. Because of that, if this is the total area, then number of atoms per unit area, that will be area 0.5 by 0.866 a square. Due to that, we will get 0.58 by a square atoms per unit area. Now, second question, let us take another illustration to understand this. For that, if we take a problem that prove that in a cubic crystal, the direction HKL is perpendicular to the plane HKL. So for that, if we take the intercepts of HKL plane along the three directions, X direction, Y direction and Z directions are R1, R2 and R3. Then these intercepts can be written as R1 will be written as vector A by H, R2 will be written as vector B by K, and R3 will be written as R1 by R1 equal to C by L. Now, if we take a vector capital H, which will be equal to the H into vector A plus K into vector B plus L into vector C. In the direction, then the direction HKL, and if this vector is representing the direction of HKL, and R1, R2 and R3 lie in the plane of HKL, then H into R12, you see R12 is what? R12 is this one between R1 and R2. So due to that, H into R12 will be written as vector H. The value of vector H is this one, so we will put this, and R12 can be written as vector R2 minus R1. So, and the value of R2 is vector B by K, and the vector value of R1 is vector A by H. So due to that, we will get B dot B minus A dot A. Now we know that for any simple cubic system, B is equal to A equal to C. So we have changed B by B dot B as A dot A. Now A dot A minus A dot A will be 0. Like that, if we put, if we find H into R3, this is H into R3. Just recall what is R13. R13 is what? Between R1 and R3. So due to that, we will put H, the value of H, HA plus KB plus LC into R13. So R13 means vector R3 minus vector R1. So due to that, this R3 will be written as C by L and R1 will be written as A by H, C by L. So due to this, the product will be C dot C minus A dot A. As C is equal to A, so C will be written like A dot A. C dot C is equal to written as A dot A. So A dot A minus A dot A is equal to 0. So thus we have found, we have shown the problem. What was the problem? Problem was that we have to show that in any cubic crystal, direction HKL is perpendicular to the plane HKL. If this was not there, then how we will get the dot product as 0? So this confirmed. Now interplanar spacing between lattice planes of cubic lattice. Interplanar spacing, the formula for interplanar spacing we have derived in the last class. Today we will see that in the lattice planes of cubic crystal, what is the interplanar spacing. So at first we have taken the simple cubic lattice. This is simple cubic lattice. In any simple cubic lattice, the Miller indices of three planes are 100, 110 and 111. So from the formula last day we have learned DHKL is equal to A by under root H square K square plus L square. Now this 100, this means this is the value of H, this is the value of K, this is the value of L. So we'll do that. We will put here A and the value of H is 1, the value of K is 0, the value of L is 0. So A by 1 square plus 0 square plus 0 square, this will be equal to A. Now D110, A The value of h and k are 1, whereas the value of L is 0. So A by root 2. The value of D11, that will be what? Here the value of h is 1, k is 1, and L is 1. So we'll put these values, and this, because of that, the interplanar spacing between the lattice planes of cubic lattice D111 will be A by root 3. So thus we have calculated that. Now let us calculate it for body centered cubic lattice. In the body centered cubic lattice, there exist additional planes halfway between the planes 100 and 111. So due to that, we will be able to find out the interplanar distance. So thus for this lattice, we can write D100. This will be equal to what? Half of D110 for simple cubic lattice, because there is an additional plane in the halfway. So due to that, this will be equal to 1 by half, because we have written half of D110 of D100 of simple cubic. D100 of simple cubic will be what? A by h square, that is 1 square, k square, that is 0 square, L square, that means 0 square. So A by 1, that means 1 by 2 into A by 1, that is A by 2. D110, this will be same as D110 for simple cubic lattice. So due to that, this will be A by root 2. Then again, in the BCC lattice, the plane 111 is just midway between 111 plane of a simple cubic lattice. So due to that, again we will write D11 is equal to half of D11 for simple cubic lattice. So this will be equal to 1 by 2 into A, the value of DHKL, no, HKL is 111. So because of that, this will be A by 2 root 3. So we have calculated for the body centered cubic structure also. Now for the face centered cubic structure. In the face centered cubic structure, there is an additional plane in the D110 midway. So because of that, D100 will be half of D100 for simple cubic lattice. So this is A by 2. Again, in the 110 plane, there is again a midway plane. So due to that, this will be half of simple cubic D110. So 1 by 2 of this one, A by 2 root 2. Whereas there is no plane in the midway of D11 in face centered cubic structure than the simple cubic. So because of that, this will be equal to the D11 plane of the simple cubic structure. So this will be A by the values of HK, L are 111. So due to that, A by root 3. So thus we have calculated the interplanar spacing between the lattice planes of a cubic lattice. Here for simple cubic lattice, here for body centered cubic lattice, and again here for face centered cubic lattice. Now let us solve some numerical problems so that we can understand it correctly. So for that, we have taken the first one as this is the interplanar spacing. The interplanar spacing of 110 plane is 2.2 angstrom for a cubic crystal. Calculate the atomic radius. You will have to calculate the atomic radius. So plane is given 1110 plane. So let us calculate this. This will be equal to A by h square plus k square plus L square. So this will be equal to, from that we will be able to find out A. Why? Because you see, D is given. The interplanar spacing is given. D is given 2.2 angstrom. So we will be able to calculate A. A will be equal to D into under root h square plus k square plus l square. The value of d is 2.2 and the value of h and k, that is 110. So the value of h is 1, the value of k is 1, and the value of l is 0. So because of that, 1 square plus 1 square. So this will be got as 1 plus 1 root 2, that is root 2 into 2.2. This will be got as 3.11 angstrom. For simple cubic crystal, we know that A equal to 2R. So from that, R will be equal to A by 2, that is 3.11 by 2. If this will be 3.11 by 2, then radius in the simple cubic structure will be 1.555 angstrom. For BCC crystal, it will be R is equal to root 3 by 4 into A. So root 3 by 4 into A, the value of A is already calculated 3.11 angstrom. So we'll put that and we will be able to get the value of radius as 1.347 angstrom. For FCC crystal, in the FCC crystal, we know that 4R is equal to root 2A. Due to that, R will be equal to root 2 by 4 into A. Now, A is calculated 3.11 angstrom into root 2 by 4. So we will get 1.099 angstrom. If the, let us take the another problem, just to understand this. So if we take the radius of nickel as nickel atom or Ni atom is 1.245 angstrom, calculate the interplanar distance of 100 and 111 planes of nickel atom, nickel crystal or atom. Since Ni has FCC structure, so we'll use the formula of Ni structure. Now, in the FCC structure, we have seen that R is equal to A by 2 root 2. So from that, A will be equal to 2 root 2 into R. Now, R is already given 1.245 angstrom. So we'll put that, and due to that, we will be able to find out the value of A as 3.52 angstrom. Now, D100. So interplanar distance, due to that, this will be equal to A by 1, the value of H is 1, the value of K is 0, the value of L is 0. So A by H square plus K square plus L square, that is 1 square plus 0 square plus 0 square. This is equal to 3.52 angstrom. D111. So the value of SKL R111. So due to that, A by under root 1 square plus 1 square plus 1 square, 3.52 by root 3, that is 2.03 angstrom. Now we come to know a very important relation, that is Bragg's equation. So at first we will have to know the Bragg's treatment. So probably all of you have heard about Bragg. W.L. Bragg investigated the condition for X-ray diffraction by means of model, which gives the correct mathematical results in a very simple way. He found that the direction of diffracted beams can be accounted for by making the assumptions that the X-rays are specularly means mirror-like, reflected from parallel atomic planes in the crystal, and the multiple reflection interfere, and it interferes constructively in those directions. Now it is common practice to interchange the words diffraction and reflection of X-rays. We are not going in detail for that. At first, Bragg has given for interference. Later on, this was also corrected for diffraction also. So I'm not going there. This is beyond your syllabus. But these two terms can be interchanged in the case of Bragg's treatment. Suppose the horizontal lines These are the horizontal lines. You see these horizontal lines. If these horizontal lines represents the parallel planes of the atom, okay, this is the parallel planes of the atoms, uh, which partly reflected incident X radiation, the distance between the successive planes being assumed to be d. Here this distance between the two planes is d. If we are taking this as d, and if we take that Snell's law is correct, this means the incident beam, reflected beam, and the normal are in one plane for the mirror reflection, and the angle of incidence equals the angle of reflection. The path difference for rays 1, this is ray 1 and ray 2. So the path difference between the rays 1 and 2 reflected from the two adjacent planes. You see, it is reflected from the upper plane and this is reflected from the lower plane. So these are the two adjacent planes from where the ray 1 and ray 2 are reflected back. If planes is the length PQR, so this will be equal to what? P, if we extend it in this direction, so this will be PQR, because these two, the length of 1 and 2 are same from this point. So extra path which is traversed by the second ray will be PQR. So this is the path difference between the rays 1 and ray 2. Now the rays reflected from adjacent planes will be in phase and their amplitudes will reinforce to produce a strong reflection. Only if this path difference is equal to the integral number n of wavelength lambda. So the Bragg's condition will be equal to 2d sine theta equal to n lambda. This is known as Bragg's law. N being the order of diffraction. This n is order of diffraction. D is the distance between the two successive planes. Theta is this angle, and lambda is the wavelength of the light used. So on the basis of this, we can say that there are only certain directions theta in which the reflection of a given wavelength lambda for all parallel planes add up in phase to give a strong reflected beam. And let us solve some numerical problems over this Bragg's equation. So for that, the first numerical problem we have taken as the spacing between principal planes of sodium chloride crystal is 2.82 angstrom. It is found that the first order Bragg reflection occurs at an angle of 10 degree. What is the wavelength of the rays? So for that, we will use 2d sine theta equal to n lambda. So lambda will be equal to 2d sine theta by n. Now the value of d is given. This is 2.82 angstrom. So 1 angstrom equal to 10 power minus 10 meter. That is why we have converted it to meter. So 2 into 2.82 into 10 power minus 10 into the value of sine 10. So we will get 0.98 into 10 power minus 10 meter. 10 power minus 10 meter is equal to 1 angstrom. So because of that, this will come out as 0.98 angstrom. Now let us take another example. X-rays of wavelength 0.71 angstrom are reflected from the 110 plane of a rock salt crystal of lattice constant A equal to 2.82 angstrom. Calculate the corresponding glancing angle for second order reflection. So here we will have to calculate the glancing angle for second order reflection, that is n equal to 2. Wavelength lambda is given 0.71 into 10 power minus 10 meter because angstrom. So interplanar spacing between 111 plane, the value of h, k and l are given. So d is equal to a by this one. The value of a is also given. This is 2.82 angstrom. So we are not converting this angstrom. That will be calculated in terms of angstrom. 2.82 by 1 square plus 1 square plus 0 square. 2.82 by root 2, that is 2 angstrom. Now we will apply the Bragg's equation. 2d sine theta is equal to n lambda. So from that, theta is equal to sine inverse n lambda by 2d. Now sine inverse, the value of n for second order, so n equal to 2 lambda, that is given 0.71 angstrom, and 2 is 2, and the value of d we have calculated as 2, so 2 into 2. So because of that, theta will be equal to 20 degree and 42 minute. So we come to know that glancing angle will be 20 degree and 42 minute. So now it is requested to you to solve a large number of problems, and we will discuss these problems in the theoretical class or during the live classes. Here the solid state physics uh, completes the vector, and the video lectures is completed. Now for further studies and to strengthen your knowledge, you can go to all these books. These are very good books and you can go through them. Now, thank you.